Hello and welcome back to the Astro-Imaging channel. Tonight's topic is by Bob Buckheim. It's Astro-Imaging for Science. But before we get into that, today's image of the day is by John Talbot, and it is M78. And I'm going to jump over to that image and give John a few seconds to talk about it. Screen share over, and I believe you can see it. If you can see it, go right ahead. John, you could go ahead if you're there. I don't know if you can hear me. Can you hear me, John? John Talbot?
John, can you hear us? Go ahead and start speaking.
John, can you hear us? John? All right. Go ahead, John. I think you were just trying to talk. If not, I'm going to have to jump it short. I do apologize. No, I don't think we can hear him. All right. Well,
no.
I do apologize, but it's a great image of M78 by John Talbot. If we do get a chance, I'll try and get a blurb from him, but I don't see it. So tonight's topic. Oh, first of all, I see a couple viewers in the room already. So ask your questions in Q&A, and we'll call them out to Bob. And if you want, you can subscribe or join us live, and we'll take your topics as they come. But I am going to hand it right over to Bob, and Bob can start us off.
Well, hello, everyone. Okay, Adam, can you are you seeing my desktop?
I'm seeing your desktop, and I can hear you.
Fabulous. Well, good evening, everyone. For those of you who don't know me, my name is Bob Buckheim. I, a few years ago, completed a really wonderful 35-year career as an aerospace engineer and manager. And so now I'm indulging my childhood dream of being an astronomer. So here's the obligatory picture of me in my backyard observatory. Adam and Alex thought that it would be a good idea for me to talk a little bit about astro-imaging for science, since the real reason that I got a CCD camera was one of my friends got me all excited about doing light curves of asteroids. So they invited me under the delusion that I was some kind of an expert and that maybe some of you would be susceptible to the same disease that I caught. I guess I am a sort of an expert, but bear in mind, in my old field, the definition of an expert is a guy from out of town with PowerPoint slides. So that's the deal. When we talk about doing astro-imaging for science, the first thing that we need to dispense is the problem of, if I'm going to do that, won't I need expensive, sophisticated equipment? Lots more cables on my telescope, special software and advanced education and quantum physics and calculus and things like that. And the answer is actually no. Unless you really want to get captured by the dark side of amateur astronomical science, you're going to be able to do real scientific research with the equipment and the skills that you already have. If you can make a halfway decent astro image, then in the same amount of time, maybe less time, you can do something like this. This is a plot of the brightness of an asteroid as a function of time. And from that kind of information, the professional astronomers who have more math skill than I ever had can transform that kind of photometric information into an actual three-dimensional shape of that asteroid, which on your image appears as an anonymous point of light. So this is the kind of thing that got me excited about the idea of using your backyard telescope and CCD camera in the service of real scientific research. And so the theme is, you can do real science in your backyard, mostly in photometry and astrometry, using the equipment that you already have, whether that's a telescope and a CCD, whether it's a DSLR and a telephoto lens with the software that you're probably already using to take and reduce your images, Maxim DL or the equivalent, and using the skills and the knowledge that you already have for making astro images. Photometry deals with the question of how bright is it. And it's the primary tool that's used to study variable stars, nova and supernova, asteroids, and a variety of other sort of unknown transients in the sky. Astrometry deals with the question of where is it. It's the primary tool used to study double stars and to figure out the orbits of newly discovered asteroids. The most important step in making this transition from conventional astro-imaging into doing science is to just give it a try. If you're doing planetary images with your video camera and Registax, that's a perfect setup for doing high-resolution astrometry on double stars, for example. My experience is that if you take a few steps that I'll talk about and make your first attempt at either a light curve or an astrometric measurement, a double star, or something like that, your first attempt probably won't succeed perfectly. But I think you'll find that the problems in it are pretty obvious, pretty straightforward to correct, and odds are that your second attempt will be perfectly successful. So what I'd like to talk about is some special wrinkles about taking your images, doing the image reduction, doing the image analysis, which is where the science lies. Most of these things will be familiar to you, but they're maybe a little bit different than what you're doing with your conventional astro images, and there's a few special features and considerations depending on exactly what setup you're using, whether you have an anti-blooming or a non-anti-blooming CCD, or if you're using a DSLR or a single-shot CCD. Any of those can provide good scientific data, but you need to understand a little bit about their peculiarities. So let's start with taking your images. There are two things that are absolutely critical in the taking of images for scientific purposes, and those are linearity and spatial sampling, and I'll talk a little about those. The use of filters is also important sometimes, but it's nowhere near as critical as the concepts of linearity and spatial sampling. Everybody probably knows that one of the wonderful features of our CCD or DSLR cameras is that they are linear sensors. The signal that you get out, the number of ADUs in each pixel, is directly proportional to the number of photons that came in. And that proportionality is quite accurate in even pretty inexpensive cameras, up to a point. Characteristic curve that all of our imagers have is that the peak ADU count on a star image or the number of ADUs in your flat field is proportional linearly to the number of photons that came in, up until that curve starts to, instead of going straight up, it starts to bend over a little bit. And at that point, you really don't know from the ADU count what the brightness of the target is. It's critical to keep the signal from your science target and any reference stars in the image below the point where that curve bends over. Keep them within the linear range, because if your ADU count or the target brightness gets out here, you really don't know what the actual brightness of the target is. It's not too complicated to understand for your particular setup where the system departs from linearity. You probably already know the full well depth of your camera, for example. If you just do an experiment either with your flat white box or a star field, take a series of images at different exposure levels. Look at the ADU counts on either a star image or the average in your flat frame. And as the exposure gets longer, more photons came in, the signal will go up, and you'll be able to see exactly where that curve starts to bend over. That's the limit of the linear range of your sensor. For a typical 16-bit non-anti-blooming CCD, expect that linear range will be somewhere in the 40 to 50,000 ADUs, maybe a little higher. And all that means is keep your signal on your target and any reference stars below that number. On the other hand, if you have an anti-blooming CCD, and remember the feature there is the chip has some separate gates and wells on it who are designed to bleed off charge from each pixel as it gets fuller and fuller, but has not yet reached its full well capacity. So charge starts bleeding off a little sooner. That's good because it gets rid of some of those blooming spikes and other artifacts in your CCD image. But it's problematic because instead of that typical non-anti-blooming curve, which is tends to be very straight right up until it starts to bend over. The typical anti-blooming CCD characteristic curve is more like the purple line here. It'll tend to start deviating from a nice linear straight line at maybe a half, maybe 2/3 of the full well depth. That's not a problem. It just means that you need to make sure that you adjust your exposure so that your target is not up there in the nonlinear range of the camera, but down where it's still linear. This problem of linearity and the associated limitation on dynamic range for CCDs, whether it's an anti-blooming or non-anti-blooming, tends to not be much of a problem for the vast majority of targets. If you imagine, Adam, can you see the little cursor on the screen?
Yes, I can.
Okay. If you imagine that you have a target brightness that gives you a signal here, and the target, it's a variable star, it gets brighter. As the brightness moves up and down here, you're staying in the linear range, but once you get to here or here, now you're deviating from linearity in the system, so that kind of limits the dynamic range. You can monitor a target that's brightness is changing from here to here, but not all the way out to here. For the typical 16-bit CCD imager, that's really not much of a problem. But for DSLRs, that is something that is really, really important to be aware of because their dynamic range is much smaller than the typical CCD imager. Here's an example of what the characteristic curve of my Canon EOS DSLR looks like. That's a 12-bit camera, which means that it can read out about 4,000 ADU when the well is full and the pixels are completely saturated. If you look at the characteristic curve at an ISO of 100, usually the lowest setting on these cameras, you can take good scientific images. You're in the linear range from here, up to about here. On my camera, that's about 3,000 ADU, and at that point, the characteristic curve starts to bend over, so you're no longer in linear range. If you've got a target that's giving you, say, 4,000 ADU, you really don't know how bright it is. It might be this bright, might be that bright, you don't know. It's a little counterintuitive, but for photometry projects with your DSLR, you're almost always going to set yourself up for ISO 100. It's a little counterintuitive because your targets are faint. The pictures are going to look horribly washed out and uninteresting. But what happens if you go to an ISO 200, 400, 1600? The characteristic curve changes as shown here. And if you look at that ISO 400 curve, if your brightness changes from here to here, a pretty small amount, you know, suddenly you're already over the saturation limit or the linear range. So your dynamic range in brightness measurements is really tiny. If you've set your variable star, you know, here, it's nice, good signal at the on that ISO 400 curve, and it gets just a little brighter. It's up here in the nonlinear region. Whereas if you did the same thing on the ISO 100 curve, yeah, your signal is still okay. The picture looks kind of ugly and washed out, but you're in the linear range. You're getting enough signal to make a good measurement. And if that target gets brighter, you're still in the linear range. Or if your reference star is significantly brighter, it's still in the linear range. So I always encourage people to use ISO 100, maybe 200, but that's really the way to go. Those of you who are aficionados of DSLRs will understand part of what's happening here. When you increase the ISO, you're not increasing the signal-to-noise ratio. You're changing an amplifier so that it increases both signal and noise in the image. So you're not generating any more information. You're just amplifying signal and noise, and here at the expense of what amounts to a reduced dynamic range. I'm going to mention under the image processing charts that it's also really important, once you've taken a linear image like this, don't muck up the linearity with some of the processing steps. Well, that, on a DSLR, that applies right back at when you take the image. Always take raw images. Those are almost completely unmolested by any of the processing software in the camera. So it's a CR2 or CR star if you're a Canon camera user, or if it's a Nikon, it'd be an NEF or something like that. Never take JPEG images for your science projects. I don't think anybody really understands the equations that are in that JPEG compression algorithm, but I guarantee you it totally messes up any dream of seeing a linear response out of your camera. So that's the only wrinkle with DSLRs. You can do really, really interesting photometry projects with DSLRs, and I'll show you an example or two later.
Bob, could I interrupt you here for a minute?
Yes.
We've tried some new things getting people in and out of the hangout room, and we understand that there are probably some people out there that are trying to get in and can't quite get in. We don't know exactly what the story is on that, but Adam and Josh are working on that. For those of you who are out there, I believe you can still get in on the YouTube. Follow us on the YouTube and go ahead and ask your questions over in the Q&A and the comment sections on the YouTube, and they'll be coming in here. As far as I can tell, as of right now, there are no questions related to your presentation so far. I'm enjoying your presentation, but and we'll continue monitoring for if any other questions come in. Okay?
Okay, great.
So,
thank you
very much.
Okay, so that's the linearity story. The other subject that I mentioned is spatial sampling. That's your image scale, say in arc seconds per pixel, and that's a little easier to understand why it's important if you think of astrometry. If you think of, I'm trying to identify the precise location of this star image in my field of view, say in terms of its pixel coordinates, coordinate number 200 in the x-axis and 520 in the y-axis. If you look at the example on the right side of the screen, where you have that star image and really big pixels. I think some people prize those 24 micron pixels because on a nebula you get much better signal and signal to noise ratio than you do if you have those teeny little 6 micron pixels. But for the scientific imaging, as I say, think in terms of measuring the position of the star. On that example on the right side, you can absolutely say that star is somewhere inside this pixel, but you can't say where. what you'd see in your image is a nice bright square pixel here and then zeros all around it. So you know it's in there somewhere, but you really don't know where it is. On the other hand, if you have a situation like is shown on the left side, where you have small pixels, that same star image, first of all, you obviously get a benefit because with smaller pixels, you've got a more accurate ability to locate that star image. But more importantly, with a situation like this, you can determine the intensity centroid of the star image, and that means you can locate the star to a fraction of a pixel size. Tenth of a pixel is pretty easy with a decent signal and a decent star image. It's a little more complicated to understand why that's important and useful in photometry, where you're trying to measure the brightness of the signal. Because after all, if you look on the right-hand side, however many photons are coming in, they all fall on that pixel. On the left-hand side, if you add up all of those pixels that are seeing starlight, well, that's the same number of photons, but it's not quite, because there are gaps between the pixels that are not sensitive to light. So in the situation on the right-hand side, if that star starts to move over a little bit, some of the light falls in the gap, and hence the intensity that you measure is being modulated by the position of the star. And similarly, on every pixel, there's a little bit of non-uniformity in the response of the pixel. There's parts of that pixel that are a little hotter than others, whereas if you have a well-sampled image, as that image moves around, the percentage of the light that's falling between pixels pretty much the same, because wherever falls off on one side is picked up on the other. And because you're averaging over a multitude of pixels, any individual pixel non-uniformity becomes much less important. Now, it's not a big deal to figure out where your system stands here. If you know the size of your pixels in meters and the focal length, the effective focal length of your imaging setup in meters, you can do the calculation. The equation is shown here. The pixel scale divided by the focal length times the magic number 206264 equals the angular size of that pixel in arc seconds. For most of us, certainly in my backyard, the best star images that I get have a full width half max of 2, 3, sometimes 4 arc seconds, and so if I can provide a pixel scale somewhere in the half an arc second to 1 arc second, then those star images are well sampled, and I'm perfectly in this range. If you discover that your normal imaging setup has pixels that are larger in an angular sense, maybe you got 2, 3, 4 arc second pixels, there's a few things you can do. First off, make sure you're not binning. It's almost never useful to bin your images when you're doing these science projects. If you have a focal reducer in the system, take it out. That'll give you a change in image scale and reduce the size of your pixels. In a pinch, you can add a Barlow to make your pixels even smaller. And I hope that doesn't force anybody into either buying a new camera with smaller pixels or buying a new telescope with a longer focal length. I think in most cases you'll find that there's an easier solution to addressing this requirement. If you're using a DSLR, this problem of spatial sampling becomes even more problematic.
Bob, can I interrupt you for a minute with a question about sampling?
You bet.
So how does it work if you are trying to take an image where you are actually, I guess, oversampling the resolving power of your telescope? Is that okay to do, or what are the consequences of doing that?
Yeah, in a sense, that's exactly what you're doing on the left side of the screen here, and that's what you want to do. If you're so fortunate that you actually have diffraction-limited star images where you can see the airy disk and the rings, the only way that you're going to see that is if your pixels are smaller than the Airy disk. So that's a good thing.
So you can't actually oversample the resolving power of your scope. That's fine.
Yeah, and you want to. In fact, if I think if we've got guys online that are doing planetary imaging, where you are doing the lucky imaging and selecting and stacking images, I would bet that that most of those people are using effective pixel scales of 1/4 or 1/10 of an arc second per pixel. Because you want to make sure that the sampling is not the thing that's driving the ultimate resolution in your image.
Okay.
So yeah, the only drawback, of course, is as you get smaller and smaller angular size of the pixel, like in the the typical situation in my backyard where I might have a 3 or 4 arc second star image and 1/2 of an arc second pixel size. Well, that means each individual pixel is only getting a 1/10 of the light that's coming from the star. So you're going to have to increase your exposure, take longer exposures, but that's easy to do in principle anyhow, and it accomplishes the goal of making sure you have full fidelity in the resulting image.
Great, thank you.
Okay. Now, as I mentioned, if you're using a DSLR, you've got this kind of interesting problem. DSLRs are single-shot color sensors, which is really neat for a lot of purposes, but it's a little bit of a problem for some of these science projects. Now, this example is pretty unrealistic, but imagine the situation where your star falls cleanly on one of the blue sensitive pixels of your Bayer mask, and because of the project you're doing, you're going to ultimately want to de-Bayer that image and only look at the green spectral band. Well, that star is going to completely disappear in that de-Bayered image. Now, I say that's kind of an unrealistic example because your cameras have anti-moire filters that are designed to mitigate this effect. But nevertheless, it happens to some degree. If you're doing photometry, you're going to want that star image to be large enough so that no matter where it moves around on the image, you're getting a complete color sample of the star. Imagine we're looking at Betelgeuse, and you sit it on that blue pixel. It's going to be relatively faint, and then a little bit of guiding error moves it over to the red pixel, and suddenly it gets much brighter. Well, Betelgeuse didn't change. It's just the spectral response of your sensor that changed and gave this spurious photometric variation. Also, if you're doing some kind of astrometry project, so you're trying to figure out exactly where the star is, you need to get that star image pretty big so that as you de-Bayer or deal with the change in apparent signal versus position because of the color of the star and the spectral response of the Bayer mask, you're going to have to really blow up those star images. So here I've de-Bayered the image. The target, the star image, is still pretty big, so I can still centroid the position of the star. I can get a reasonably good photometric signal. What that means is for your DSLR images, you're going to want 5, probably preferably 10 pixels full width half max on your star images. Those stars are not going to be points of light. They're going to be big, ugly blobs. But what we're looking for here is not a pretty picture. We're looking for scientific information. When I'm doing photometry with a DSLR, I frequently put in a pretty significant controlled defocus so that the stars are those nice big blobs, but it eliminates a lot of the artifacts that come from the Bayer mask. Filters. Most of you are probably used to using your LRGB filters to take your color images. The standard scientific image filters are the Johnson-Cousins UV-VRI filters for photometry. It's less important to be filtered at all doing astrometry, although there's a few reasons that you might want to do that. But you don't need to rush out and buy a set of Johnson-Cousins filters if you want to do photometry or astrometry. For some purposes, you want to at least get the Johnson V-band filter. That's kind of the green filter. AAVSO insists that anything put into their database be either Johnson-Cousins V-band or the DSLR G-band. It turns out the G-band on DSLR cameras is really, really close to Johnson-Cousins V. Now, why is that important? Well, imagine that we're studying Betelgeuse, and I'm going to take some images tonight, and you take some images tomorrow night, and we're going to be concerned with, did the brightness of Betelgeuse change? Well, if I'm imaging through an R-red filter, I get a signal, Betelgeuse is this bright. Tomorrow night, you image through a B band or a blue filter, and you're going to go, man, it's nowhere near as bright. But of course, that has nothing to do with Betelgeuse. What that has to do is it's always going to look fainter through a blue filter than it does through a red filter. By demanding that everybody uses essentially the same spectral response, it's a lot easier to line up the data from different people, different observatories, different epochs, because you don't have the confusing and confounding problem of everybody using a different spectral band. That's not critical for everything. It's usually a good idea to use some kind of a spectral filter. If you get excited about astrometry and double star separation and position angle measurements, atmospheric effects encourage you to narrow the spectral band that you're looking through. But hey, it can be kind of any spectral filter. You know, use your conventional imaging G band or the R band, or if you have a Johnson-Cousins V, use that. And it turns out there's also a surprising number of projects where unfiltered, clear, no filter imaging is the standard practice for asteroid rotational light curves. Asteroid colors don't change much. The reflected light is almost always the color of sunlight. And so there's no real benefit, no real information to be gleaned by putting in different spectral filters. You get a better signal level, better signal-to-noise ratio if you image without a filter. So most asteroid rotational light curves are done with unfiltered light. Faint variable stars like cataclysmic variables also tend to be done unfiltered. In that case, simply because you don't have very much light, these tend to be faint targets, and you want to do your images at a pretty rapid cadence. Cataclysmic variables change brightness noticeably on a time scale of 5 or 10 minutes, and so you need to take, maybe 1 minute exposures on that 15th magnitude target, and you can't afford to give up any light. So the standard is to do unfiltered imaging. Johnson-Cousins V is nice to have, but it's not absolutely required for a great many real live science projects.
Bob, we do have a question coming in. David, I think, is in the room, so he can ask it himself. But what about Sloan filters?
Yeah, good question. The Sloan filters are becoming increasingly common in amateur photometry projects for a couple of reasons. First of all, they're available at about the same cost as the Johnson-Cousins filters, and because of that wonderful Sloan survey, you have a complete celestial sphere full of very well characterized stars that you can use as photometric references. So I'm seeing more and more people using Sloan filters. They're a good choice. They give you, if you're doing things like variable stars, pulsating variable stars where the temperature and hence the color is changing as the star pulsates. The Sloan filters are a little bit narrower band than the Johnson Cousins, and they're a great tool. Was the question more complicated than that?
No, that was it. Thanks, Bob.
You bet. Okay, that is everything I wanted to say about taking the images. Now that you've got your image, you need to do the normal image reduction, just like you do for any other CCD or DSLR image. Do your bias, dark, and flat frame correction, like always. Do that. But then after that, keep in mind the critical requirement that you don't mess with the linearity that you gathered when you took that image. You can do anything to the image that is a linear process. So if the equation can be written as A plus B, you're okay. If you discover that your signal levels are a little bit low, and so you want to sum 3 images to goose the signal, that's fine. If you want to average images to goose the signal, or do median combine in order to get rid of that cosmic ray, that's okay. If you took short exposures because your mount's tracking and your guiding is not great, so now you've got a series of images and you want to do a shift and add, that's okay. But do it after you've done your bias, dark, and flat correction on the sub-images. But don't ever do anything that involves non-linear processing. None of the sharpen algorithms, no deconvolution, no unsharp masks, no auto-flatten of gradients. None of that is allowed. Now you've got your reduced image, and it's time to do the analysis. And this is where the science comes in. And there are some really, really wonderful special purpose software for different science projects. But I don't think you need to rush out and get any of those and learn how to use them while you're doing your first few experiences and deciding whether this science research is for you. Most of the Astro-Imagers I know are using Maxim DL at some point in their processing. Maxim has a fabulous routine for differential photometry. Use that. At some point, you get excited about variable stars or rotating asteroids. You might want to take advantage of some of the special features that are in MPO Canopus or VFOT, the AAVSO package that I think is free online to AAVSO members, or AIP for Win, which is an excellent package with a lot of neat capabilities. If you get excited about astrometry, you can do good differential astrometry with Maxim DL and Excel. If you've got one of the levels of Maxim where you can cross-match your image to a star chart like in the sky and thereby read out the actual RA and DEC of each star in the image, that makes some of the astrometric analysis even easier. If you get excited about astrometric projects, orbits, double stars, MPO Canopus, again, has some great features. Astrometrica, I think, is one of the most popular programs for the asteroid tracking guys. And Reduce by Florent Los, French double star researcher, is becoming, I think, the de facto standard among the double star guys. But you don't need to move into any of that software until you get excited. Maxim DL will do what you need for beginning projects. So here's an image of some stars, and let's imagine that we're going to start doing our analysis of that image. One of these stars is our target. One of them is a reference star that we've selected in the frame. Photometry deals with what's the difference in brightness, and that's going to involve how many total ADUs did I collect from each star when I sum up over all of the pixels that have any sensible starlight on them. If, on the other hand, say maybe this is a double star and I'm interested in the difference in position, And then I'm going to be interested in what's the intensity-weighted centroid position of each star. Both of those involve counting up how many photons, how many ADUs did I collect from the star. And that's deceptively simple. But if you take a close look at, and here's an image of one star on the focal plane. It's properly sampled with tiny pixels. And let me pick out just one pixel. And you think about, where did that pixel collect signal from? Well, it collected electrons from dark current, but we've subtracted those out by dark subtracting. It's collected photoelectrons from the star, but it's also collecting photoelectrons from the sky. And so we need to somehow unravel the sky photons from the star photons. And that's easy to understand when you look at one of these pixels that's off at the edge of the star image. But obviously, even the pixel that's in the dead center of the star image is also collecting photons from both the star and from the sky glow. So the way Maxim or any other photometry routine deals with this is it'll let you put a measuring aperture, a little circle around that target star. So you make that circle big enough that it collects all of the light that you're getting from the star, but not too big, so you're not collecting too much starlight. The software will then add up how many total counts are inside that little measuring aperture. So it's adding up both star photons and sky photons on all of those pixels, because you can't tell, any particular photon, where did it come from? It's just a photon. Then the software will allow you to establish what's called a gap, and then you put in a third ring that's called the sky annulus. And the thing about the sky annulus is there's no star in there. So when you add up all of the ADUs from all of those pixels in that annulus, those are sky counts only, which means that if I take all of the counts in the measuring aperture, that's star plus sky, and I subtract the counts from the sky aperture, because that's sky only, what I'm left with is star ADUs only. That obviously you have to account for the fact that maybe your measuring aperture has a different number of pixels in it than your sky annulus, but your photometry software will do all those calculations for you. Your job is to pick the size of the aperture of the sky annulus and place it accurately over your star.
Bob?
Yo.
Is this a good time for questions?
Sure.
We've got a couple coming in on Q&A. The first comes from Jack, and he asks, can you explain binning if it's appropriate at this time, what effect it has on your work and things like that?
Yeah. Let me go back to the sampling discussion. Okay. Remember on the left here, we've got tiny pixels and a relatively large star image, and that's good. The star image is well sampled, and I can calculate its centroid accurately. I can calculate the total photometry signal from it accurately. If you bin those pixels, like in this example, if you binned it 3 by 3, you'd end up with the situation on the right, which is undersampled. So I never recommend binning. Take the signal level hit and use unbinned images while you're taking the images. If for some reason it's a good idea to bin, do it afterwards during processing.
And just to amplify on that, we don't know exactly who is listening. Some folks have never heard the word binning. So we want to make sure that you realize that binning is just getting 2 or 3 pixels in each direction. So a 3 by 3 grid would give you 9 whole pixels. And you just add them together in the software. The software takes care of that, and your camera knows how to do all that stuff. So that's what binning is. But whether you'd use it in scientific applications, Bob says, nah, it doesn't really have a good application in science.
Yeah, I've never seen a situation where it helps. There's plenty of ways it can hurt.
Okay. Michelle has a question. When you were talking about filtering in particular asteroid light curves and things like that, you said that quite often you don't use a filter. No, it's unfiltered instead, or you use a clear filter. Luminance filter is the equivalent of for these purposes. Would it be the same thing?
Yeah, yeah. In fact, I don't know if there's a difference between a clear filter and a luminance filter. There may in the luminance filter be a either a red or a blue roll-off. I don't know, but the idea is use whatever filter you have that gives you the maximum amount of light through. And so luminance filter is perfect, or if you've got an empty slot in your filter wheel, you can use that too. You may not want to go through the dramatic refocus that entails. So luminance filter is great.
Okay, hang on for a second. There are two ways to ask questions in this stream. I haven't looked at Josh or Adam. Have you looked in the other stream? Are there any questions?
There are none in chat right now.
None in chat, no.
Q&A's got some, chat doesn't have any, and you've answered the ones in Q&A. And for those of you who just may be tuning in and you haven't been in the on the Astro-Imaging channel before, only a certain number of people can actually fit into the room. Everybody else gets to listen on YouTube, and you're welcome to listen, you're welcome to make comments, and you're welcome to ask questions and answers depending on how you're doing it there. We're monitoring both the questions and answer stream and the comment stream, and if you make comments in either one of those two places, we'll try to ask your questions for you. Okay, thanks, Bob.
You bet. Okay, so we're back. We've done our photometric analysis on the star, and the approach to astrometry, where you're interested in the centroid of the star image, goes exactly the same way. You'll set a measuring aperture, and your software Maxim, for example, will subtract sky counts. It'll calculate the intensity centroid of that star, and it'll tell you that it's at x coordinate 200.3 and y coordinate 520.6. To a fraction of a pixel, because you have that well-sampled image, and so the intensity centroid can be accurate to probably 1/10 of a pixel in most cases. Now, in the case of photometry, the other term that you'll hear is differential photometry, and that's the way, boy, probably 95% of all photometric projects, both amateur and professional, are done. If you measure a single star and I got 2,000 ADUs from it, well, what does that mean? And if an hour later I only got 1,500 ADUs from it, well, does that mean the star got fainter, or does it mean that the little bit of thin cirrus cloud went by, or does it mean that when I took my first image I was pointed straight overhead, and when I took the second image, I was down near the horizon, so atmospheric extinction was different? The way you deal with all of those problems is by differential photometry, which means I go through that measurement of the total ADUs from the star on a single image, and I look at both my target and a comparison star. Because if the thin cirrus comes through, well, it's going to affect target and comp star identically. If the atmospheric extinction changes, because now I'm looking down near the horizon, again, both of those stars are going to be affected identically, so they'll both get 10% fainter. And that means that the difference in brightness between target and comp is unaffected by those atmospheric effects. So you calculate, you go through everything that was on the previous chart. You know how many total ADUs are coming from the target. You know how many are coming from the comparison star. You've eliminated the sky, so now you can say, hey, the brightness ratio is the sum of all those star ADUs from the target divided by the sum of all of the star-only ADUs or photons from the comp star. So you can now say, my target is twice as bright as my comp, regardless of changes in exposure, changes in atmospheric conditions, etc. Now, of course, we're astronomers, so we would never work in intensity ratios. We always work in magnitudes, but that just means that you apply the magnitude equation, and now I can say my target is 0.7 magnitudes brighter than the comp. And again, your photometry software will do all that for you. It'll tell you the delta magnitude between target and comp maximum. If you hover an aperture over a star and click it, it's telling you the magnitude on a arbitrary scale, and you take the magnitude of the target, magnitude of the comp, subtract them, and there you go. Now this works almost perfectly for relatively narrow field of view images like your typical CCD or DSLR through a telescope. If you use a DSLR with a relatively narrow focal or short focal length lens, so you have a wide field of view, life gets a little more complicated because the atmospheric conditions over on one side of the field of view might be noticeably different from atmospheric conditions on the other side if the other side of the field is 20 or 30 degrees away. There's ways to deal with that, and in many projects it's a small enough effect compared to the variation in your target you're looking for that it's not a critical feature. You get all excited about photometry, you'll learn how to compensate for that as you go. So now you've taken your images, you've learned how to do the image reduction and the analysis, you've got the scientific data out. What kind of projects can you do? Well, I mentioned that I got started in this because a friend of mine got me all excited about the rotational light curves of asteroids. Now here's the deal. If you look at, let me go back to the prior slide, there's all those stars in there. One of them might be an asteroid. I don't remember what this was a picture of, but what an asteroid looks at like in your image is just any one of those stars. It's an unresolved point of light. The only way that you can tell it's an asteroid is if you take an image now and then 10, 15 minutes later you take another image and you blink the two of them. You'll see the asteroid has moved a little bit along its orbit, so it'll jump back and forth. But aside from that, an asteroid is just an anonymous point of light in the sky. But suppose you aim your system at that asteroid, you take a 1 or 2 minute image, you get a picture like I just showed, and you do that over and over again. 1 or 2 minute images, bang, 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 all night for 6 or 8 hours. And then you tell Maxim, here's the asteroid, here's my a reference star, and you can pick pretty much any reference star in the image that's not saturated, not outside the linear range of your sensor, and it'll do the differential photometry of asteroid target minus comparison star. What's the brightness? And it'll chunk through all of that night's images, and it'll get a number, a delta magnitude in each image, and then you plot delta magnitude versus time. And you get a curve like this that says that asteroid changed in brightness by 4/10 of a magnitude. That's a lot. You could probably see that with your eyeball. And then it got brighter again, and then it got dimmer again, and then it got brighter again. And there's an enormous amount of information encoded in that curve. The simplest to understand is that if the asteroid is a potato-shaped kind of thing, and it's rotating, well, when you see it face on, it's going to be bright because it's got a large surface area. And as it rotates and you see it, kind of pointy end on, well, the surface area just got smaller, so it got fainter, and now you're down here at the bottom of that light curve. And then it kept rotating. It went from that way to back to face on. It got brighter again, and the period at which that happens, well, that's the rotational period of that asteroid. So that little point of light now is betraying itself as a rotating object, and it's obviously not spherical, because if it was a perfect sphere, then the brightness wouldn't change as it rotated. It turns out then, if you imagine it as a potato or a football or a triaxial ellipsoid, if you're mathematically inclined, and you imagine that thing rotating, well, the delta magnitude from brightest to dimmest is telling you something about the aspect ratio of that object. So now that point of light is telling you that it's, maybe 50% longer in one direction than it is in another. So you're getting an idea of the shape of it. The fact that this minimum is dimmer than that minimum is telling you something about the nature of the shape of the object also. When this end is pointing to you, somehow it's giving you a larger projected area than when this end is pointing at you. So maybe there's a hill or a squashed end to the potato or something like that here. And you can also see on that second downward slope, see there's a kind of a little inflection point there. That's the evidence of topography on this object, a hill or a valley that's changing the light curve from what you would see if it was a nice smooth ellipsoid. So there's all kinds of information that comes out of that. And that's the kind of information that planetary scientists use to understand rotation rates, understand surface texture, the scattering process of the surface, the albedo, a series of these kind of light curves usually from several years, several different apparitions, where you're looking at the asteroid from slightly different orientations relative to its spin axis, is what they can then map together into what's called light curve inversion shape model. So you actually have now a three-dimensional globe of the shape of this object that all you can see in your image is a single point of light. So this is really, really kind of compelling stuff, and a single light curve like this is a publishable result. You write a little, do this, write a little one-page paper in the Minor Planet Bulletin, and hey, you're a published scientist now. The other thing that you can do as a good beginning project is eclipsing binary stars. We all somewhere along the line learned the idea, if I've got two stars, so if I can do this on the camera, and they're in orbit around each other, and they happen to be lined up perfectly the way I've sort of got it here, so that one star eclipses the other, and then as they go around their orbit, there's an eclipse where the other star is behind. Well, the characteristic light curve, how come I can't? The characteristic light curve might look something like this. This is the light curve of EK Coma Berenices. Took it with my 11-inch Celestron and EOS Rebel camera. I wanted to demonstrate photometry with a DSLR. You see three curves here because after I took all the images, I did the photometry process on debayered images. So there's a green, a red, and a blue light curve, and they're arbitrarily offset just to make the visual easier to understand. But so here again, you've got, if you focus in on the green light curve, it got dimmer, it got brighter, it got dimmer, it got brighter. Notice once again, one minimum is a little dimmer than the other. The period of that pattern is the orbital period of those two stars going around each other. The fact that one minimum is a little fainter than the other is telling you that one star is fainter than the other. When the faint star passes in front, that's when you get that dimmest bottom in the light curve because it's blocking light from the bright star. When the bright star is in front, you don't lose as much light because it's blocking the dim star. When you're up here, you've got a situation where both stars are shining at you. And I don't remember exactly why that happens. I'll have to go back and look at that star. The fact that the curve, if you remember what an algol light curve looks like, you see an eclipse and then a flat brightness for a long time and then the next eclipse. The fact that this never settles out to a flat light curve is telling you these stars are so close together that their mutual gravity is kind of distorting them. So there's a shape modulation in the light curve. They're kind of more like egg-shaped objects rather than spherical stars. So it turns out light curves like this, particularly if you get them in 2 or 3 spectral bands, and that's where you might use your Johnson V and a B and an R light curve to understand the brightness in the 3 bands, which is obviously related to the temperatures of the 2 stars. You can use a light curve like this to model the size, separation, shape, and temperature of this system, and that kind of modeling turns out it's not too terribly difficult with these light curves, and that's one of the few ways that astronomers can unambiguously determine the physical sizes of stars. You know, you read all those books about this star is that big. There's darn few ways other than eclipsing binaries to determine that. The other thing that turns out to be a big deal is you can imagine putting say a quadratic curve through that minimum and determining the exact time of minimum light. There's an ongoing and critical research value for most of these eclipsing binaries in monitoring the exact time of minimum light. If the system was a perfect Newtonian 2-body isolated system, you know, going around each other like this, those eclipses would happen like clockwork. Now, one period apart through all of eternity. It turns out with most of these systems, if you do that mapping of their times of minimum light, and you plot over years or decades what's called an O minus C, an observed time of minimum versus the expected or calculated time of minimum based on the period of the orbit, there's a lot of variation that happens, and that variation can betray the evidence of a third star in the system that's pulling the eclipsing pair back and forth from the gravity of that third star. It can betray mass transfer between the 2 stars. They're that close that the mass from one is streaming on the other. It can betray magnetic field interaction between the stars. There's a lot of neat science, and so one of the important things that AAVSO, the American Association of Variable Star Observers, does is collect these times of minimum light and provides that data to the stellar research community. The other thing that's kind of fun about both asteroids and EBs like this is you might not be able to read the time scale on this graph, but the total graph is about 4 hours long. This represents one night of data gathering. So you can get real instant gratification if you're wondering, oh, would I like to do photometry? It's really cool to take images for one night, and then you do the data reduction, and the next day you actually see there's something happening out there at that star. Double stars. Back in the 17 and 1800s, double stars were the thing for professional astronomical research. They've, to some degree, gone out of style, and the professional community more and more relies on amateur astronomers to maintain a cycle of measurements of the relative positions of double stars. It turns out of the I don't know what there are, 250,000 or more double stars in the Washington Double Star Catalog. That's the primary archive of the International Astronomical Union of double stars. Of that 250,000 or more stars, the vast majority of them, we still don't know whether they're orbital systems or they're just optical doubles, 2 ships passing in the night that are one's far away and one's close by, and they just happen to be along the line of sight. Well, the only way that you tell that is you monitor their motion over time. And your CCD imager is a perfect tool for doing that. And here's an example of the sort of thing that happens. This particular double star called MLB 102, the first measurement that was made, the discovery measurement, was in 1906. The separation between the bright star and the fainter star at that time was 4.8 arc seconds. And the position angle, which is the orientation of its position relative to celestial north, was 185 degrees. So the faint guy was almost due south of the bright guy. Then Come 1918, somebody measured it again. And what had happened is the faint star had moved a little farther away from the bright star, and its orientation on the celestial sphere had rotated by about 20 degrees. And then one of those things happens that is very common in this business is nobody looked at it for the next almost 90 years until one evening it showed up on my observing list in '07. And now the separation had grown quite a bit, and the angular orientation had gone quite a bit. And now that you've got 3 data points, you look there and you can kind of see there's a curve going on, which is one of the things that betrays the probability that we're dealing with an orbital pair here. And you come back in, well, about now, 10 or 20 years, and you'll probably find that that star is out here somewhere. And you keep that up for 100 or 200 years, and you can map out its orbit. And orbits are one of the few ways to unambiguously define the mass of the stars. So there's a lot of really fun science that can happen here. The other thing that your CCD imager can do with astrometry is not exactly science, but if you know a high school kid or maybe a college undergrad who wants to do a science project for the science fair, here's one that I got involved in a couple of years ago that really blew me away at the idea that this could succeed in my backyard, and that is Barnard's star. Take an image of Barnard's star every few weeks or every month while it's up, and in the course of a month, you can see its proper motion. If you look at the chart on the left on this, Barnard's star moves, proper motion is over 10 arc seconds per year. That's 1 arc second per month. And if you've got 1 arc second pixels, that's a whole pixel in a month and a half. And so what you see here in the red dots are the position measurements that we made, 1 year and the next year, and you can see that son of a gun has moved a long way. And that got me wondering, well, suppose we goose the cadence of our observations a little bit, and let's try to map out the full motion, taking images throughout from the time it's just rising just before the sun all year until it's setting right after sunset. Back out the orbital the proper motion by a linear fit, and what's left is what's on the right side curve here. That's the parallax ellipse of Barnard's star. So you can measure the distance to Barnard's star from your backyard. There's no science in that. Everybody knows what the distance is, but the idea that you can do it in your backyard is one heck of an interesting science fair project. And as I say, it boggled my mind that it could be done pretty easily with my 11-inch telescope and my ST8. I think, resources. You get excited about some of these science opportunities, and you want to do some of that. 2 resources that I encourage you to check out are the American Association of Variable Star Observers. They keep the database. They accept your measurements, photometry of variable stars. They've got a great semi-annual meeting. Usually one meeting each year is kind of in the eastern U.S. and one in the western U.S. They've got a lot of good educational packages there if you get interested in variable star photometry. The other is the Society for Astronomical Sciences. Full disclosure, I'm one of the trustees of SAS. We have our annual symposium in June, 11, 12, and 13 this year in Ontario, California. This is the premier gathering of both amateur and professional astronomers who are interested in small telescope science. You'll see a lot of asteroid, binary star. There's going to be a workshop, educational workshop on speckle interferometry with small telescopes. More and more of the guys are getting interested in spectroscopy. Check out the SAS website. You can see videos of the technical presentations from the last 2 or 3 years to give you an idea of the pretty amazing things that people like you are doing in their backyards with their Astro-Imaging. And if you want to get some of the educational workshops, those are available. Send me an email. Most of those come at a price, $50 per DVD. But I think you'll find that they're well worth it. And if it isn't, send me a note. We'll give you a refund. The other thing that no talk like this would be complete without is a little unbridled capitalism and shameless self-promotion. So if you're saying to yourself, I'd like to do some of this, but I think I really need some kind of a book that'll help guide me through the steps and exactly how to do all this. That's why I wrote The Sky is Your Laboratory. It's the manual for doing the kind of projects that I've described here and quite a few others for the backyard scientist who's interested in making the step into providing research data to the professional astronomy world. Astronomical Discoveries You Can Make Too is scheduled for release in the middle of this year, and it's a compendium of projects for science students. The idea is, if you think about the history of astronomy, it's built on a series of seminal observations. You know, we saw the way the sun goes around the sky and the seasons change, and then we learned about the planetary motions and the stars and how they vary and how far away they are. And it turns out that all of those seminal observations, everything that Ptolemy and Hipparchus did, and Galileo and Newton, all those things, you can do them in your backyard, many of them without a telescope, just a DSLR and the standard 50-millimeter lens. So that's what this book is about, is how to replicate those projects. That concludes my prepared remarks. If we have any further questions, I'll be happy to try to answer them or make up something.
First of all, thank you, Bob. That was a great presentation. I'm going to buy one of your books because I can't wait to try some of that stuff out. I even have some from prior images of Barnard's star that I was hoping to do exactly what you said, measuring the motion of it. Had no idea about the parallax. You can actually you can find out the distance of Barnard's star. I mean, that's crazy.
It's amazing.
Yeah, I'm kind of blown away by that. I had no idea. Even the being able to measure the shapes of asteroids by the light curves. That's another thing that kind of blows me away.
Mm-hmm.
We're so smart these days, and the equipment that's being dropped into our laps, especially with DSLRs, it's just amazing what amateur equipment can do.
Yeah, the DSLR is an amazing tool, and there's one of the other things that is a really fun science project with your DSLR. No telescope, just put it maybe on a tracking mount or a tripod, 50-millimeter lens, and do a light curve of algol. Some of the astronomy clubs that I've talked to, you ask, everybody knows about algol. How many of you have actually seen it go through its eclipse? And nobody has. Everybody knows about it. Nobody's seen it. A couple of nights with your DSLR camera, and you can map out the eclipse of algol, and it turns out you can see the secondary eclipse, which is something that astronomers didn't discover for like almost 200 years after the initial discovery of Algol's period.
Very interesting. John is asking a question now. Is there a minimum pixel size for CCDs that you can recommend? He's thinking of repurposing some older equipment. Or should he say maximum pixel size? So I think he's wondering the limits of sampling, whether he's looking at another sample.
It's totally dependent on your focal length. Let's see if I can get all the way back to that chart, but if physical pixels are in microns, pick a focal length that will give you, say, nominally 1 arc second. pixel size. My C11 with a 6.3 focal reducer on it, feeding my ST8, which has 9 micron pixels, is almost exactly 1 arc second per pixel. If you have a 24 arc second pixel, and as many of the larger cameras do, then you just need a longer focal length to get the pixel scale, angular scale down.
And he says perfect. Thank you.
Certainly. And yeah, don't be afraid to use a Barlow if it comes to that.
Yeah, there's a few rules that you're breaking when it comes to deep sky imaging that are probably just very appropriate.
Oh yeah, and that's one of the things that you will see is you follow the rules for linearity and sampling, and your images are the artist in you is going to say, oh, that's ugly. But remember, the goal here is scientific data, not beauty. There's a different kind of beauty when you plot the curve.
I remember one time I was selling equipment for my club, and somebody wanted to buy a C11 that the club had for sale, and I mentioned to him that it had some, I forget what problem was, and he says, oh, I don't care about that. I'm just using it for science. I don't care about that pretty picture stuff.
That's right.
You don't have to worry about your equipment nearly as much. Even, I think, some of the tracking issues and stuff like that. You should be as good as you can get all the time, but it's not pretty picture stuff.
Yeah, Alex makes a good point. For astrometry, obviously, sweet star images are pretty important. But for photometry projects, a little bit of image trailing, that's not a big deal. Make your measuring aperture a little bigger to collect all the starlight. Some of the, I don't think Maxim does, but MPO Canopus will allow you to have an elliptical measuring aperture. So if your stars are trailing a little, just line the ellipse up to that. For super accurate photometry projects, it's not uncommon in the professional world to defocus the image. Exoplanet transit light curves, where the transit signature is maybe a 0.5% drop in the light, very often intentionally defocus so you get the maximum averaging over any pixel non-uniformity. So if you've got one of those 24 micron pixel cameras and you just can't get the image scale down to 1 arc second for bright targets, you can defocus.
Well, Bob, I understand that we can actually see evidence for exoplanets from our backyard.
Oh yeah, yeah. There's some exoplanets in the Kepler field and a few others scattered around the sky where the transit signature is 1 or 2% drop in light. Now that's only 0.01 or 0.02 magnitudes, but carefully done backyard photometry, I've seen 0.75 of a percent drop on exoplanet transit. I wouldn't recommend it for your first photometry experiment, but it's absolutely doable. And remember, I mentioned that idea of timing the exact time of minimum light of an eclipsing binary star. Well, with exoplanet transit, there's an ongoing need for timing the ingress and the egress and the duration of the transit to search for other planets in that stellar system. And that's absolutely doable in your backyard with little experience and care in your photometry.
Another cool thing.
How affected are you by weather? Does a few cirrus clouds screw everything up, or what?
Depends on the project. Most photometry, you want it to be pretty clear. You get even the least little bit of cirrus, and you start getting differential color effects between your target and your comparison star, where the the cloud is, it's scattering more blue light than it is red light, and that can really honk things up. If the targets are really bright, you can get away with it, but a clear night is pretty much required for photometry. On the other hand, bad seeing doesn't really hurt your photometry.
What about the moon?
The moon, if the target you're looking at has a fairly sizable delta magnitude, if you're looking for a magnitude change of a few tenths of a magnitude, if you can stay 30, 40, 50 degrees away even from the full moon, it's not terrible. Astrometry, double stars, asteroid orbits, are much less affected by a little bit of cirrus or a little bit of moonlight, but they're more affected by seeing. So there's if you've got a night of great seeing but it's a little hazy, do your double star project. If it's really crystal clear but the seeing is terrible, do your photometry.
And if it's crystal clear and the seeing's pretty good and the moon's not out, time for the pretty pictures again.
No, that's when you go after those really faint cataclysmic variables.
I was going to ask about the cataclysmic variables. You said over a 5-minute period you can see changes?
Yeah, it's a little challenging because they tend to be kind of rare and by implication kind of far away and kind of faint, but that's one of those areas where the professional astronomers who study cataclysmic variables really rely on the worldwide network of amateur astronomers doing photometry, because when the star is that dynamic, you need to keep it under continual surveillance 24 hours a day for maybe a week. And if you've got a network of observers, a few here in the West Coast and somebody in Hawaii and someone in Japan and somebody in Europe, you can keep it under surveillance continuously with no gaps for several days. And those kind of light curves, the professionals can't get any other way. If you're intrigued by cataclysmic variables, Google the Center for Backyard Astrophysics. That's the network of guys that are doing that kind of photometry. The Center for Backyard. I think it's cba.org. And they've got a great network of observers and a good set of resources describing what these stars are and why they're challenging, and that's the central repository for the data. Joe Patterson, Dr. Joe Patterson, is the leader of CBA.
We just got the link, cbastro.org. Perfect.
Yep. John Callum asked a question. John, are you in the room? Can you turn your mic on and ask it yourself, or is that a different John in there? There's a couple of Johns. Is there a minimum pixel size for CCDs that you can recommend? Oh, no, I'm sorry. I'm reading the wrong one. Where'd I go, guys?
In imaging,
go ahead. Take it, Adam.
In imaging, we shoot for 1/2 of our image scale. Since tracking doesn't seem as important for photometry, do you have a rule of thumb for guiding error?
No. It's for most photometry projects, the guiding error is really kind of a secondary issue. I'd be embarrassed to show you some of the images that I've gotten great photometry on, where the guide star was faint and the targets were kind of wandering around. But as long as you can set your measuring aperture to collect all of the ADUs or photons that came from the target, a little guiding error is not a killer. And if you have the occasional image that's really terrible, you just throw it out.
Yeah, so it's interesting. It basically doesn't matter because you're just counting the photons that have struck the sensor. It doesn't really matter where they've landed.
Yeah. It's in some ways it's a lot more forgiving in terms of the imaging.
No apologies necessary, John. Yes, he doesn't have a mic. For all you guys out in Q&A, you guys are welcome to post up any questions you have. I haven't seen any new ones. Or maybe I did. Is differential imaging for asteroids much much the same for comet discovery?
I don't have any personal experience with that, but I know the Japanese fellows who have done a fabulous job of discovering nova are taking great advantage of DSLRs and pretty normal lenses, fairly wide fields of view, and you take images tonight, images tomorrow night, and basically you blink them or subtract them, looking for what's new or changed. I would think that you could do the same with comets. With all of the professional sky surveys going on looking for the killer asteroid, it's harder and harder for an amateur to discover a new asteroid or a new comet. Interestingly, it doesn't seem like the NOVA search has been that adversely affected. I think most of the asteroid searches stay away from the Milky Way. So if you want to discover a nova, that may be the direction to move.
Very interesting. I was actually going to ask that. That's novas and possibly supernovas as an opportunity for actual being the first to see something. Those are probably your best bets.
Yeah, Tim Puckett has what I think is the most successful amateur supernova search program, and that's become a real factory. He's got his robotic telescopes that take images of, I don't know, 50 or 100 galaxies every night, and then he's got a team of people who examine the images and blink, tonight from last night, and they've got, I think, several hundred supernova discoveries to their credit. The trick there seems to be that you're working a game of numbers. Supernova in any one galaxy doesn't happen very often. What's the number? Maybe one a century. So you need to look at a lot of galaxies every night. And you're competing with things like the Palomar Transient Factory, which is doing that exact same thing, hitting every galaxy they can every night.
So how do you report data? Say you found an asteroid or comet or something like that in your data. How do you report it or determine if it's already been found?
That's an excellent point. None of these results have any value unless they're somehow communicated to the professional research community. For the professors, it's publish or perish. For us, it's we will eventually perish, and our data will go with us unless we get it into the hands of people who need it. And depending on the nature of the object and the nature of the data, there's different ways. For asteroid light curves, the thing to do is publish a little one-page paper in the Minor Planet Bulletin that says, here's the asteroid, here's the light curve that I saw, and then duplicate, download your photometry data to the asteroid light curve database. ALCDEF. I don't remember exactly what that stands for. And that way it's now in a master database that the planetary scientists do in fact interrogate when they're looking for light curve data on their objects. If it's a variable star, the AAVSO is the place where you archive your photometry data. There's applications on their website where you can just download, push your photometry into their database, and they'll accept it and keep track of it. For a new discovery, you found the new comet or you found the new supernova, there's a procedure at the International Astronomical Union, the Central Bureau for Astronomical Telegrams. There's a procedure for submitting the new discovery there. Rule number one on that kind of a deal is if you've discovered something, get one of your buddies to confirm first before you report it. There are a myriad ways that you can discover something that either is already well known or is an artifact. One of the most kind of amazing stories happened to me well, this must have been 10 years ago or so. I was out at our club observing site out at Anza with my 16-inch Dob, and one of my friends on the next pad was doing some imaging through his 11 or 12-inch Schmidt-Cass, and he came over in the middle of the night and said, "Bob, have you taken a look at Galaxy blah blah blah?" And I said, "Well, as a matter of fact, I was just looking at it. It's looks gorgeous." He said, "Did you see anything funny?" No, I didn't. And he took me over to his telescope, and we looked at the image he had taken, and by golly, there was a comet right next to that galaxy. And I said, "Well, that's amazing. Let's, in 15, 20 minutes, let's take another image." He says, "I've already done that." And it's moving from image to image. And we went back and we looked at it. It was bright enough. It should have been plainly visible in the Dob. And we couldn't see it. We could see the stars around it. We couldn't see this comet. A couple of days later, he called me sort of sheepishly and said, "I figured out what it was. It's not a new comet." What was happening was the way his telescope was pointed was this way. And down in the valley below us, back here, was a neighbor's street light, and the light from that street light was coming in, catching a corner of his dew shield, scattering into the optics, and showing this really diffuse, distorted spark of light on his focal plane. And of course, as the telescope tracked, that little spark of light moved. So that's why you always do a double check before you report your new discovery.
We're checking the comment streams. I'm not sure we've covered everything that Bob was and somebody else was talking about over into the questions. They seem to be coming back and forth. But I think you've talked about comet discovery. You've talked about Tim Puckett's work that he does and stuff like that. And I think that was the main thrust of that. Those questions they were having.
By the way, if anybody's interested in getting involved with Tim Puckett's supernova search, I'm pretty sure he's always looking for additional people to do data reduction. I'm not sure what his situation is regarding telescope time and taking images, but Tim's going to be at the SAS symposium in June. So if you'd like to meet him in person, come on out to that.
Great. You guys out in Q&A on the stream, you guys should ask your questions now, if you still have them. One more. Got another. I'll just link in chat.
Go over in Q&A. We've got everything I think that's been in there. You guys got comments covered?
Yep.
There's been a couple of links added under comments for how to get a hold of Comet Watch and Supernova Search. Justin added a few things there. And CBA Astro, I think we talked about that. So I think we've talked about everything in the outside stream for those outside the Hangout.
Okay, great.
Yeah, it was a great presentation. Thank you, Bob, for coming by and offering to do this for us. I'll remind our viewers out there that Bob has a couple books that if you guys want to pursue this further, it's great to look in. I have The Sky is Your Laboratory. I don't remember the title of the other one.
The other one is Astronomical Discoveries You Can Make, and that's scheduled for release middle of the year. Although Springer is taking advance orders now if you want to make a commitment.
Hey, Bob, could you, recruit a few of your friends over at SAS and whatever, and maybe they'd like to give a presentation here on some of the specialties, maybe 45 minutes or so on asteroid curves or something, get a little more into detail on it. We're always looking for good presenters. Maybe you'd like to come back with something that you're particularly interested in. You've given us a really good overview of everything and told us that we've already got the equipment. We've already got what we need if we're on the Astro-Imaging channel. All we've got to do is start doing some of this stuff. Well, go a little more in depth as to what some of the things you do and how to work some of this stuff, things like that. You know, every couple of months,
Yeah.
be back here and give us something.
Yeah, that might be kind of interesting to work through either an asteroid or something like that. Yeah, I'll put that on my calendar and see if I can
Great.
come back in a couple of months.
Great.
You're welcome whenever you'd like.
Okay, thank you.
You know, Justin's asking, are there one more question. So are there particular needs that the scientific community has right now?
Well, I think I've talked about most of the areas that are the most common amateur involvement. Asteroid light curves, the planetary sciences pretty much totally depend on amateur scientists for that. Variable stars. If you check out the AAVSO website, you will see a continual stream of campaigns where a professional astronomer needs data on a particular star, usually in a situation where they're doing Hubble telescope or Spitzer telescope data on that object, and they want visual band photometry to put it in context. Cataclysmic variables, there's ongoing series of projects and very dynamic stars needing photometry. And the wider double stars, again, it's almost totally the purview of the amateur astronomer today to keep doing what Herschel started back when, monitoring the motion of these stars. There's probably others that I forgot. Oh, lunar meteor impacts. If you've got a video set up and you're doing planetary images, that's perfect for recording the impact flashes when meteors hit the moon.
Hmm.
Who knew?
Who knew? Yeah, that's an interesting one. Is that a frequent? Can people capture them frequently? Because I know I heard of one maybe a year ago.
I wouldn't say frequently, but it turns out I think they're far more common than anybody imagined. 20 years ago, Dr. David Dunham started mentioning the idea that when a modest meteor hits the moon, it ought to make a splash and a flash, and even in the professional community, he was kind of poo-pooed, and that's the dumbest idea anybody had ever heard. And then during one of the Leonid meteor storms, he and a few guys set up video cameras looking at the dark side of the moon and saw a couple of pinpoint flashes that lasted a fraction of a second. And the one that really shocked everybody was this flash at that location was recorded simultaneously at 2 locations 100 miles apart. So it wasn't noise, it wasn't an artifact, it was a real thing. And in response to that, the ALPO, the Association of Lunar and Planetary Observers, stood up a project to monitor, particularly during meteor showers, monitor the right portion of the moon, and NASA stood up a program, and I think everybody's been sort of boggled by the meteor impact activity on the lunar surface that had never been seen before.
I don't know. It's stuff like this that makes you want to live forever. So you
Yeah.
can see every discovery that's ever made, because
See how it's going to turn out.
Discovery. That's what we're given. But yeah, this was a great presentation. Thank you so much, Bob. Like Alex said, you are welcome back anytime. I see we have 16 viewers on there, so you guys have one last chance to ask your questions. I'm giving you about a minute before I end the session.
Adam, can we give John another shot? Maybe he's figured out whatever was happening with his image earlier, and remember he was.
Oh yeah, that's a great point, John. If you want to give it a shot, you could go over your image again. If you're still there.
All right, I'm here. Can you guys hear me?
I can hear you. Share your image.
Okay, great. Thank you very much. Sorry, Adam. Yeah. So we had some issues earlier. Anyways, this image of M78 started out as a project I did back in January. I took a HA shot of this, and I saw a whole bunch of hydrogen alpha signal in the background, and I thought, wow, this is kind of neat. So I shot during the full moon, I guess over about 5 or 6 nights, and then did the normal LRGB images when the moon disappeared towards the end of January, early February. The image is comprised of about 27 hours worth of exposure from a suburban location where I'm at. Got a lot of light pollution here, so it was kind of interesting trying to get rid of all the gradients, but obviously it worked out okay. So I used a 130 millimeter refractor, a QSI 583 camera, and PixInsight to process the image. So yeah, thanks a lot for accepting it, and I really appreciate it a lot. Appreciate it.
No problem. Thanks for sharing it. It's a great image. No intentional defocus in this image, which is something. It's funny because I kind of came into this thinking, oh, we do a lot of similar things to the science people. I remember watching a special on one of the professional observatories, and I was watching them take calibration frames, and I thought to myself, oh, I'm almost doing science. But then you hear the things that separate us, and they're kind of significant things. One's appropriate for one, one's appropriate for another, but really, really cool to just hear the presentation in general. So I do want to thank you all for coming. I'm sorry, I'm going to take my camera back somehow. There we go. I do want to thank you all for coming out in the room. Going to check Q&A just one last time. I don't see any new questions. Remember, next week we have Lauren Keller on for a demonstration of PixInsight, and the following week on Paramount, or on, I should say, the Paramount Imaging Workflow. So, again, thank you guys for coming, and we'll see you next week.